Hello and welcome to the Phoenix Space LaunchPad Challenge. My name's Dr. Simon Foster. I'm a space scientist at Imperial College London, and I'm here today to give you an overview of the challenges and issues facing a potential mission to Mars. And hopefully through this talk it'll give you some ideas about an entry that you could place into the competition. Now, you may have seen that there are 3 overriding topic areas for any entry that you may wish to submit, and these are in engineering, sustainability and social organisation. And hopefully through this talk I'm going to touch on all 3 of these topic areas, and hopefully it will give you somewhere to start building your idea, your concept, your solution around. Okay, so let's get started. So one of the main things we've got to look at is the spacecraft itself. How are we going to get our astronauts and our equipment to Mars and through the harsh vacuum of space? So originally when astronauts went to the moon, they actually went on a very large rocket. It was called the Saturn V rocket, and this was what's called a multi-stage rocket. So most of the rocket actually didn't contain the astronauts and their equipment. Most of it was fuel and actual boosters, as you can see in this image here. You can see here, hopefully, you've got the different stages of the rocket. You've got each one is a thruster, and as that fuel ran out in that section, it was ditched, and the engines in the next section would ignite, and once the fuel in that section was ditched, it would go on and on and on, and it was called a multi-stage rocket. Okay, what's quite strange is it's only right at the top here, you can see here, this top bit here, that actually contained, remarkable as this seems, that actually contained any of the payload, the astronauts, the equipment that we sent to the moon. So how are we going to send astronauts to Mars? Because actually sending such a tiny amount into space means we're going to need lots and lots and lots of rockets. Is that efficient? Is that the correct way of going about things? Well, one of the proposed ideas has been put forward by SpaceX and Elon Musk, and his idea is to use something called the Big Falcon rocket. And actually he's already started testing this. So you can see here, this part here, they've already started testing this. SpaceX have started testing this. This is the top end of the rocket. And a lot of this actually will contain astronauts and equipment going to Mars. And this will be placed on top of a bigger reusable rocket, which you can see here. And this will be launched from Earth, and the top bit will detach and fly straight onto Mars. The bottom part will come back down to Earth. And this top part will fly to Mars and actually land there, and hopefully take off again, bringing astronauts back to Earth. And one of the issues you might actually have to face is, how will you actually refuel your rocket on Mars? Because actually these rockets are using methane. Now methane we can get on Earth, we can actually tap it from the ground, from we find a fossil fuel source. But on Mars, as far as we're aware, there aren't any fossil fuel sources. However, there is water, and this is what I'm going to speak about later, and there is carbon dioxide. And water and carbon dioxide can, through a chemical process, produce methane gas and oxygen. So that's one possible way, and it's a very intelligent thing that Elon Musk and SpaceX have done, is that they're using methane to power their rockets. Now, you could take this approach and have a big rocket, one big rocket and spacecraft going to Mars. However, another thing you could use is the modular concept. You would continue with the rockets we've got now, launch smaller parts piece by piece into space, and actually build it. Build your craft in space that will take your astronauts to Mars. And we've seen this happen with things like the International Space Station. So here you've got a picture of the International Space Station as it started out, and over the years it grew to be a lot bigger. And this is something we could do. We could build a spacecraft in orbit around the Earth, piece by piece by piece, and then launch it on to Mars. And this is one potential idea, and we call it the modular concept. Here you've got each different pieces, and this is SpaceX also tried this out, and a few other groups like Bigelow Space, NASA, the European Space Agency. have all thought about this concept, because this way is actually a way of very simply building a very big spacecraft that could take your astronauts all the way to Mars, and they would have space to actually move around. So there's lots of different things you can think about getting your astronauts all the way to Mars. Now, one of the problems of launching astronauts, going through space and actually getting to Mars, is G-force or gravity. Now, to get your astronauts into space, the rocket needs to be travelling at 11,000 meters per second. That's 11 kilometers a second. That's a colossal speed. Now, to get them up to this speed, you're going to have to accelerate the rocket and the astronauts very, very quickly. And this produces a huge strain on the human body called G-force. You may have been in a car, on a train, on a bus, any vehicle. And as you speed up or go around a corner, you feel yourself being pulled backwards, around the corners like this, and that's G-force. Racing car drivers experience this a lot. Okay? Now, to test this out with our astronauts, you can put them in one of these. This is called a centrifuge. It's a bit like a roundabout that you have at a park. You spin your astronauts around, spin them, spin them, spin them, spin them, spin them, and then hopefully, after a period of time, you basically can weed out which ones have the strongest hearts and lungs and stomachs that will make the best astronauts. And what's really interesting is that inside here, you can actually have cameras. So we've got cameras inside here that we can see, okay, and these are the astronauts, and we can see these, and as you can see here, they've got all this soft squishy stuff for them going round. You see the G-force up in the top right hand corner. This tells you how many times the pull of gravity they're feeling. Okay, so a lot of this is 5 to 6. Now, you can see all this soft and squishy stuff is pulled back. You can see a lot of them are really struggling to breathe. And they're really struggling to breathe because your lungs get squashed. You get compressed as you're accelerated. Also, the blood gets pulled down to your feet. So a lot of these people are passing out, they're fainting. It's called G-lock, gravitational loss of consciousness, because your heart can't pump the blood up to your brain against the pull of gravity because it's so strong, and you can pass out. Now this is a problem. All these astronauts are going to be fine, because all these pilots, because in the middle you've got something called a dead man's stick, and it's a stick that you hold, and then when you faint or pass out, you let go, the machine slows down again, it goes back to normal gravity, which you can see up here. Your heart pumps blood back up to your brain, and you come back round, you can see. Okay, so they're all okay. But you don't want that happening to your astronauts when they're launching, or when they're trying to accelerate to escape the pull of the Earth's gravity, or indeed the get off of Mars and the pull of the Martian gravity. Also, as you can see here, you've probably had your breakfast, lunch, dinner. You've got a big sack of food and water in your stomach, and being span around like that can make you sick. So you also need your astronauts to have a very strong stomach. Now, that's on the launch, but there are other issues facing our astronauts, because in space, astronauts are weightless. There's no gravity. So does that cause any problems? Well, you've got one issue of launching and lots of gravity, high G-force, but in space, nothing. Now, you would think this would be quite nice. Okay, and you can see here, this is Helen Sharman and her co-pilots on Mir, and that was nearly 30 years ago. It was 30 years ago. That was in 1991, May 1991. They launched up the first British astronaut. She's my hero, so I'm going to use her pictures. But this is Anatoly and Sergei with her, and you can see in the middle, you've got Anatoly here, who's on an exercise bike, because in space, actually, without the pull of gravity, your heart can get a lot weaker. It doesn't need to pump so hard to pump blood up to your brain because there's no gravity. So this means the heart muscle can weaken. Also, all your muscles, your arm muscles, your leg muscles, it's called atrophied. It's when your muscles get weaker because basically they're not used. Now, that can be a problem on long missions into space. Okay. Also, your bone density can get a lot weaker as well, because without the pull of gravity, your bones don't need to be as strong, so they can weaken as well and become brittle. So this is a really big problem. So I've got two pictures here. One of Helen Sharman over here, and she was only up in space for a couple of weeks. Now you can see here that when she got out, she seems fine. She's been helped out by the people that come to the site where the pod has landed, but she's fine. She's smiling. One person, two people have helped her out, but she doesn't really need any help. After a couple of weeks in space, her heart hasn't really degraded that much, her bones haven't degraded that much, and her arms and leg muscles haven't degraded that much. However, on the right hand side we have Sergei. Now he'd been in space for several years, because while he was in space, the Soviet Union that ran the Mir space station collapsed, and they couldn't afford to bring him down, so he had to stay up on Mir to keep the space station going. He was up there, and I think he was up there with Anatoly, his co-pilot as well. They were both up there for a while. I think Sergei stayed up there longer, and he was up there I think for several years, or I think he was up there for a year, sorry. And in that time obviously his heart had got weaker, his arm muscles had got weaker, and his bone density had decreased. And you can see when he comes out, he isn't smiling quite as much as Helen over here, is he? He looks quite pale, he's very sweaty, because his heart muscles, his lungs, his arm muscles are all having to work, suddenly work a lot harder just to do the things that you and I take for granted, walking around, sitting. It was very hard for him. And you can see he needs 3 people to help him out. He actually had to be carried away by stretcher. You could see he's smiling away at the time. He was fine, but he had to be carried away by stretcher because he was so weak. Now, I met him a couple of years ago, and you can see he's still alive. He's perfectly fine. Here he is. I'm very excited to meet him. As I say, I've kind of lost control of my facial muscles. I'm kind of snorting. But it was a great pleasure to meet him and honour. He's a really great guy. So he's fine. He's still alive. But he went up several times more after this as well. But you can see the damage on the human body that long duration space missions can have. And it would take a minimum of 9 months to get to Mars. So think about that. What impact could that have on the human body, and how could we overcome that? Not only that, so one of the ways I should say is artificial gravity. You've been on a roller coaster, you've been on a roundabout. You feel high G-force on this. Is it possible that perhaps we could create artificial gravity on our spacecraft? So this is a mission I worked on, an idea, in that you could actually send out some sort of huge weight on our spacecraft when it gets into orbit around the Earth, and actually start spinning the craft. And as you're spinning the craft, you're creating artificial G-force. You see, we've seen it around that. And our astronauts inside would actually not feel weightless anymore. They would actually feel a pull of gravity on their body, and it would keep their heart muscles and their arm muscles and their bone density strong enough for when they get to Mars. Another big problem is that when you get to Mars, Mars gravity is only about 40% of what it is here on Earth. So your weight will be a lot less. So over a long duration, a long time being spent on Mars, what will this do to your body? Because basically it's just like, in space you're weightless, but on Mars you're only going to weigh 40% of what you do on Earth. Again, your heart doesn't have to work as hard, your bones don't have to be as strong, and your arms and leg muscles don't need to be as strong. What impact could that have upon our astronauts? These are things we need to solve, need to think about, and these might be areas that you may need to work on or want to work on. Now, another issue is something that I love. I'm a space scientist. I study the sun. Is space weather. Believe it or not, space weather is a thing. Okay, and we're going to start looking more and more in the future at the space weather forecast. We need to understand what's happening in the sun and the space environment for the impact it has upon the Earth, satellites and astronauts. And if we're going to Mars, which, as I say, could take 9 months, space weather could play a big impact. Okay, because when we went to the moon, we didn't know about space weather, and we only nearly missed, which I'll talk about in a minute, some real problems. So this could be an issue in the future. So on Earth, we constantly get bombarded from space by stuff called cosmic rays. Now, cosmic rays are particles and radiation coming from the sun, other stars, and even other galaxies. Now, we have the atmosphere and the Earth's magnetic field to protect us from cosmic rays. So down here on Earth, we call it background radiation. It's very weak, so it doesn't really impact our body too much. But even on Earth, you can see here, this is called a cloud chamber. You can detect cosmic rays down here on Earth, and I've done this experiment. It's really interesting. In space, you get hit by an awful lot more cosmic rays and radiation. Now, where the International Space Station is, it's still inside the Earth's magnetic field, so that offers some protection. But going to Mars, there isn't much protection. What could we do about that? Now, on top of that, the sun occasionally has storms on it. And these storms can throw out huge bursts of radiation and energy called solar flares or coronal mass ejections. You may have heard of these, okay? Now, these are huge, enormous bursts of radiation and particles, and these would be incredibly damaging for human beings. Okay, so we really need to be careful of these. Okay, we really need to be careful of these. And what we've got here is something called LASCO, the I'm trying to remember, Large Angle Spectral Coronal Observatory. Okay, and what it's done is it's effectively made at an eclipse. It's placed a little disc over where the sun is, over the camera, so you can actually see what's happening around the sun. Okay, so we can see all the storms going off, and you can see all these storms going off here. And this satellite is about a day ahead of the Earth. Okay, so can you see all that blast in there? That's all radiation and particles hitting the satellite. And this is an early warning system, because we know if it hits the satellite that's ahead of the Earth, it's also going to hit the Earth a day later. It's slightly ahead of the Earth and slightly closer to the sun. Okay, so when it hits the satellite, when the Earth gets behind it, so it hits the satellite and the Earth will come behind it, and that storm will hit the Earth. So these are really important. They're early warning systems for us here on Earth. But we need early warning systems also to protect our astronauts going to Mars, because all this radiation could hit them. These solar flares could hit our astronauts, and it could be devastating for their bodies. Okay, there was a storm in 1859, a solar storm called the Carrington Storm, that was so powerful that the aurora, which I'll look at in a second, which is normally caused by solar storms at the poles, the North and South Pole, this was so strong, it pushed the aurora down to the Caribbean, to Jamaica. Places like that could see the aurora. Such was the power of this storm. And there's famous storms in the past, but let's look at astronauts going to the moon. How has solar storms affected them, or could have impacted them? Well, there's lots of lines and bits here, but what you need to see is, can you see these grey lines? Okay, these are the missions that went to the moon. Okay, so we've got Apollo 11, the first mission, Apollo 12, Apollo 13, right up to Apollo 17 in 1972, right at the end of 1972. And these blue peaks are solar storms, and powerful solar storms. You can see one here. A really powerful storm. So let's see, in terms of radiation, what these would have looked like. So the first line I've drawn here is your average annual radiation dose on Earth. Okay, so down here on Earth, okay, this is the radiation we receive in black, and there's a couple of spikes associated with these storms, but more or less we're fine. We always get just below or just above. It's annual, so we're normal. That's safe. Okay. So some of these storms would give you, just about as much as radiation as you would get in your annual dose. Okay, so I've got here in yellow your annual dose. So some of these storms would have, in one storm, given you a year's worth of radiation. Not good, not particularly bad. You'll be all right. You'll survive. Now, some of these storms here, like this one here, if this hit here, these storms here, that would increase your risk of cancer over your life. Again, that's quite bad. Okay, we don't want to start increasing the risk of cancer just from one solar storm of our astronauts. Now, these ones here in orange, like this storm here that nearly hit Apollo 12, and this storm here that nearly hit Apollo 8, you get severe radiation sickness. That is terrible. That's when your hair falls out, your skin can blister, your nails can fall out, you'll start vomiting, being sick. We don't want our astronauts to experience that. That's really, really, really bad. And that's from a solar storm. However, it can get really bad. And this storm here, you can see, just here, between Apollo 16 and 17, that would have been, if one of those had hit the astronauts, that would have been instantly fatal. They would have died within hours of being exposed to that much radiation. Now, in Earth's orbit, as I say, we've got the Earth's magnetic field to protect us. Going to the moon, perhaps you could shield yourself behind the moon so you don't get blasted with this radiation, or you could come back inside, abort the mission and come back inside the Earth's magnetic field, because you've got a couple of days warning before one of these things hit, the time it takes for that radiation to get from the sun to the Earth or the moon. But on the way to Mars, you have no protection. So perhaps we might need to find a way of protecting our astronauts. Could it be that we just pick a right time to go? These solar storms occur when the sun's more active. The sun gets active and less active, active and less active. We can see that through things called sunspots, which is what I'm interested in, what I study. So when you have lots of sunspots, you have lots of solar flares. And when you have fewer sunspots, you have fewer solar flares. So maybe we could go, we can predict when this is going to happen. We can see here with just after a peak, maybe we could go in one of these troughs when there's fewer solar storms. But that would still mean, solar storms can still happen during this period. Would we take that risk, or do we need to devise some way of protecting our astronauts? And as I say, this is what happens with a magnetic field. All this radiation from the sun, these solar flares, get pushed around the Earth. But occasionally some of it can come down at the poles, get fed down here, and this is how we get the aurora. And this is how a magnetic field, you can see here, this is a magnet, and inside an old TV you have particles being fired at the sun. And you can see here, this is how a magnet deflects particles, charged particles, because we know a magnetic field can impact upon a charged particle, a moving charged particle. So this is how a magnetic field, like the Earth's magnetic field, deflects particles. Okay, strong magnetic field can deflect particles. Perhaps that could help. Perhaps we could devise some sort of way there. And on Earth, as I've said before, this is what we see. We see the aurora when one of these things hits the Earth. So these are super important and something that needs to be taken into consideration. It's part of the reason we actually haven't sent astronauts back to the moon and to Mars yet, because this is a huge problem which we need to solve. Now we get to Mars, we've got to live there. But let's look at the environment. Mars really lacks an atmosphere. It's got a very thin atmosphere, so you can't breathe outside. It has no magnetic field, so you could get blasted with radiation. There's no liquid water on the surface like we have here on Earth, so what problems could that pose? Firstly, let's look at the habitats. Where could our astronauts, our Martians, live? Well, perhaps we could actually use the spacecraft that go there. Perhaps we could land the spacecraft on the surface and turn these spacecraft into the habitat, into what they live in. See, these are like the landing pods that when people come back from the International Space Station, they look much like these. Perhaps you could use these, link these up, launch lots of them from our modular ship that we've had in space, and actually cannibalize that. Turn that into our living quarters. That could just be the start, but it'd be a way that we could initially live on Mars. Long term, perhaps we could build domes. You can see here our astronauts actually have to have spacesuits still outside the dome, but perhaps we could have domes in which we could live. Glass domes. And perhaps we could have something like this, huge greenhouses where we would grow plants, and we could have other domes with fuels inside, and this is our living quarters. How we're going to live there is a really big problem. It's something we really need to think about. Getting to Mars is one thing, but living there, staying there, surviving there is a big problem. Or perhaps we could do something different. Perhaps we could live underground. We could actually tunnel out underneath the Martian surface caves to live in, and actually place windows up top, and that would protect us from the harsh radiation of space. That could be one way of doing it. The UV radiation, there's lots of issues. We could send robots to dig out tunnels, advance in advance of human beings going there. And then we could live underground and just have windows letting light in. That could be an easier way of solving a problem. There are lots of issues. And also, while we're outside, we need to have spacesuits. Because Mars lacks an atmosphere. So just like in space, you still need to have a protective cocoon around yourself, because human beings can't survive on the surface of Mars. There's no atmosphere. We believe what happened was Mars once had a magnetic field. And this magnetic field protected the atmosphere from being stripped away by these solar storms. But when the magnetic field collapsed, the atmosphere over 4 or 5 million years was slowly stripped away. And so now Mars has a very thin atmosphere. It's too thin for us to survive in. One idea is that we what's called terraform the planet. Terra is Earth, so we make it more like Earth. We release lots of gases into the atmosphere, maybe oxygen, carbon dioxide, nitrogen somehow, and we make it more Earth-like. Is that a long-term possibility? So we wouldn't need spacesuits outside, we could just walk around. Is that a possibility? Is that something we could do? Now, another issue we have is water. We take that for granted here on Earth. Water's everywhere, luckily. Most of us have access to clean running water. We're very, very lucky. But on Mars, there's no water on the surface. So we may have to recycle our own water. So we pass water, we would collect it. We'd have to filter out that water so we could re-drink it, water our crops. How can we do that? Now, filtering things, actually, we can do it quite simply on Earth using sand, gravel, charcoal, cloth. You can actually do it. You can take dirty water, pass it through a plastic bottle like this, and actually you get relatively clean water out. That's a simple way. Or perhaps we could use a more complex way. Perhaps we could use something like graphene as a filter. Graphene is a wonder material. It's very strong, very flexible, and you can build sheets of it. Maybe you could build holes into this graphene through which water could pass, but the impurities couldn't. So you pour water through your filter and you get clean water out. You'd only need one layer. That is a possibility. Okay? But we need to figure out a way of getting water on Earth, on Mars. That's a really big problem. The other issue is how we need food. We can't. The more food we take with us, the more weight, the more cost, the more we've got to launch into space. We really, really, really want to, if possible, grow our own food there, because we want fresh fruit and vegetables. That's important for the human body. We need that. Okay, so we have to grow food there, but the gravity is lower. There's less sunlight. There's no atmosphere, so we can't grow it outside, and we've got this problem with water. So how could we grow food there? May we need to genetically modify crops so they could grow there, so we'd have special Martian crops. This is a really big issue. What type of crops will we grow? How will we grow them? The hydroponics involved. This is something that we need to solve. Okay. Also, for the human body and living there, and for plants, Mars, the day is almost to say the day length, the time Mars takes to spin on its axis, is 24 hours and 38 minutes. So that isn't going to prove too much of a problem. However, the Martian year is, I think, 633 days. So that's nearly double what it is on Earth. So how are human beings, how are plants going to cope with a year that's nearly twice as long as the Earth? And there's no real seasons. It gets a little bit colder, it gets a little bit warmer. How will human beings cope when the year is completely different? It's not 365 days. How will we cope there? I know that sounds peculiar, but that's a really big problem. Just the human psychology of living on another planet with a different time system. Now, how will we get energy? Perhaps we could use sunlight. But the issue there is, with Mars being so far from the sun, being a lot further out, the solar radiation's a lot weaker. It's a lot less. So will sunlight alone, will solar energy provide the energy for our astronauts for all the things they need to do. Will that be enough? Perhaps there's a different energy source we need to look at. One thing we could look at is water. Now, we believe there might be water in ice form below the surface on Mars. So perhaps we could take that water, warm it up, and we have liquid water. Now, perhaps we could use that liquid water as a fuel source. Now, that sounds peculiar. However, you may be familiar with the phrase H2O. Water is H2O. That's 2 parts hydrogen, 1 part oxygen. And weirdly, the thing about the water molecule H2O is the hydrogen is slightly positively charged. The oxygen is slightly negatively charged. So what we can do is we can take our water and with an electrical source, maybe solar, we can pull apart water into hydrogen and oxygen. Okay, and I can show you this now with this clip. If you drop a battery into water, okay, you get little bubbles, which you can see here. Okay, and these little bubbles are actually hydrogen and oxygen gas. They're pulling the electricity in the electrical source is able to pull apart the water molecule into hydrogen atoms and oxygen atoms. We could use that oxygen possibly to breathe. But the hydrogen could be stored. And the great thing about hydrogen is that when you recombine it with oxygen, you get, bang, lots of energy out. So we could store that hydrogen potentially, and then recombine it with the oxygen. We would have an energy source, just like we see here. We could even maybe use sunlight. But we can store that hydrogen, so when of a night time when there's no sun around, we would have this hydrogen, recombine it with oxygen, and we could power our cars, our lights, whatever we need on the surface of Mars. That's a really useful thing, and hopefully we're starting to use that on Earth, hydrogen power. And I think that's a really useful thing that we could use here on Earth. Now, another issue is, and this is a big thing, what are we actually going to do on Mars? We're there. Okay, we've landed there. Our astronauts are all safe and well, but what are they going to do? So we need to have a mission. Okay, perhaps we'll look at the geology on Mars. There's the Mars is home to the solar system's biggest volcano called Olympus Mons. But how did this form? How did the solar system's biggest volcano form? What else about the Martian geology that we don't we know? Is it still volcanically active? Is there liquid? Is there magma below the surface? Is it still geologically active? We believe that actually Mars has never had plate tectonics like we have here on Earth, or maybe it did in the past. We need to look at that. So the geology of Mars is a big mission that we need to look at. One area of interest is an area called Cydonia. And a long time ago when we sent probes to Mars and they sent pictures back, and we thought we saw pyramids and possibly a face on Mars. Now, this might just have been a trick of the light, but actually investigating the Martian geography is going to be something that's going to be really exciting. Just looking at the rocks, how did these strange pyramids form? That could be a really big mission. That's something we need to investigate. Another thing is searching for life on Mars. At the moment we send probes there. I think this is Perseverance. We've sent that probe there, and it's using equipment, machinery to dig down and try and find some microbes, and which is still life. It's trying to find those. But a human being may be able to do that a lot quicker. Okay, and if we find life, what are we going to do with it? Perhaps these are microbes. Are they going to be harmful for us on Earth? Are they going to be useful? We need to learn these things, especially if astronauts are going to be there, because perhaps these Martian astronauts could be damaging to us. Could we bring our astronauts back? These are all the things we need to look about on our mission. Another thing we need to think about is just the history of the planet. As mad as that sounds, Mars could have once had liquid oceans, and it could have had a big atmosphere. It could have been Earth-like. This is an artist's impression of what Mars could have looked like 4 or 5 million years ago. There could have been oceans there. Could those oceans have once held life? Okay. What was Mars once like? It's amazing to think that that could have been Mars once. A planet not that dissimilar to Earth. Isn't it strange to think about that? What happened to Earth? Where did it to Mars? Where did its magnetic field go? Where did its atmosphere go? Where did all this water go? What a puzzle. We need to find out about that. So that's one of the possible missions, and this will help astronauts and colonies on Mars integrate and work with each other, because we would have these problems that we would need to solve. Now, hopefully that's given you a brief overview of some of the issues facing a potential mission to Mars, and maybe giving you some ideas. These are not in any way, shape or form exhaustive. There's lots of other problems that you yourself can go off and search and basically come up with answers for, but hopefully this has given you a starting point. I find the possible idea of sending human beings to Mars absolutely fascinating. It's one of the things that hopefully in our lifetimes we'll see. Indeed, one of you could be the first human being to land on Mars, or be one of these early Martian astronauts. So these problems could be problems that you need to solve, you will be facing, or solutions that other people have provided for you to be able to land on Mars. So this really is something that scientists are battling with. So the solutions you come up with could in fact be incredibly useful. So I wish you good luck, and I look forward to seeing your entries. Good luck, future Martians.